Hi, this is Alan, and I want to talk to you a little bit about Henry's Law. We've already talked about the total O2 content formula, and that total O2 content formula, which was our CaO2 formula, it combined two laws, the hemoglobin times 1.34 times our SaO2, which is really our Dalton's law of partial pressures, plus our PO2 times 0.003. And this is actually Henry's law. Okay, so we have, when we look at the total O2 content in the arterial blood, which is really important to us, and we want to know how much of the oxygen is actually getting into the arterial blood, well, we have to put into play or use Dalton's law of partial pressures, and we have to use Henry's law, which predicts the amount of a gas that will dissolve in a liquid. So just knowing that, that's just one application. We use that here. We could also look at this as in the CVO2, and that would be PVO2 times 0.003, because there's plasma in venous blood too. But again, what we're looking at is we're looking at the solubility of a gas in a liquid, and it tries to predict the amount. There is a formula that Henry's law that uses. They all have formulas, and I don't make my students have to memorize the formula, but we do have this V, and it's V, which stands for the volume of gas that dissolves in a liquid at a given temperature, equals the solubility coefficient of a gas of a given liquid times the P gas, the partial pressure of a gas above a liquid. We're going to put this as P gas. Okay? So right here, we have the volume of gas, okay, that dissolves at a given temperature, equals this here. This is the solubility coefficient, okay? The solubility coefficient of a gas of a given liquid. Okay, what we're looking at here is to see how much of the gas that will dissolve in 1 milliliter of a given liquid at a standard pressure and at a specific temperature. Okay, and we can look at plasma as a good example. So we have the solubility coefficient. I'm just going to write solubility coefficient. Okay, and that is of a gas that's going to dissolve in a given liquid at a standard pressure at a given temperature. Well, how much of this gas that will dissolve in 1 milliliter of a given liquid? We're going to be looking at how many milliliters of a gas will dissolve in 1 milliliter of a liquid. So it's milliliters over milliliters. That's going to be our units, milliliters over milliliters here. Okay? And then we're going to multiply that by the pressure of the gas that's over or above the liquid. Okay, so this is the partial pressure of the gas above the liquid. Volume of gas that dissolves at a given temperature equals the solubility coefficient of a given liquid, of a given gas in a given liquid, times the partial pressure of that gas above that specific liquid. Okay? And this again is all at a standard pressure at a given temperature. Okay, well let's look at a couple of things. You know, one of the things that we look at when we do our CaO2 formula is the PO2 times 0.003. Well, where's the 0.003 come from? Well, that 0.003 comes from, it's a given or a known solubility of a gas known as oxygen in 1 milliliter of plasma. And in 1 milliliter of plasma, 1 milliliter of plasma, approximately O2, we will see 0.003, it's actually 0.023 milliliters of oxygen dissolved in 1 milliliter of plasma. If I was going to look at CO2, it would be approximately 0.510 milliliters of CO2 that will dissolve in 1 milliliter of plasma. Well, we looked at here the solubility coefficient, and well, here we got the solubility. Here, this is the amount, and then we have the partial pressure, okay, of gas above the liquid. The liquid is the plasma, so then if we look at this from Henry's law, the second part of with oxygen dissolving in plasma, okay, that is the PO2 times 0.003. Well, here's the partial pressure of the gas above the liquid times the coefficient of a specific gas, which is oxygen. And we're looking at this as 0.003 milliliters over 1 milliliter of plasma. And we can see how much oxygen will dissolve in the plasma. That was really important for me to understand, kind of put together. I mean, understand the O2 content formula. I mean, the CaO2 equals the hemoglobin times 1.34 times the SaO2 plus the PaO2 times 0.003. Well, this part up here, again, is Dalton's law, and this is Henry's. So there is a reason to learn these laws. Now, I will tell you there are a couple of things that will affect solubility. Okay, temperature has a major effect of solubility of gases in a liquid. It's an inverse relationship. As temperature increases, the solubility of the gas in a liquid decreases. And as temperature decreases, it increases the solubility. Okay. So, we know we have an inverse relationship with temperature. Temperature increases, solubility decreases. Temperature decreases, solubility increases. Well, what's that mean? How is that important? Well, let's look about it, because if we looked at the oxyhemoglobin dissociation curve, okay, and we looked at this curve and we talked about a shift left or a shift right, okay, a shift left is going to be a decreased temp, and a shift right is going to be an increase in temp. Okay? So we have shift left, decreased temp, shift right, increased temp. How do we know it shifted? We have to look at the P50, the saturation, P50, the comparison of our saturation of our hemoglobin, 50% saturated, and what is the partial pressure, which would have been 26.6. And we need to know that position, because if it shifts a little bit this way, it's shifting to the right. And if it's because of the temperature, an increased temperature is going to cause a decrease in solubility, which is going to do what? It's going to have a decreased affinity for the oxygen. Oxygen is going to have a decreased affinity for the hemoglobin molecule, as well as the oxygen is going to be released very easily from the plasma to get to the tissue. Why? Because the tissue needs it. Well, as we go to the left, the temperature decreases, and we go here and we have a P50 that's less than 26.6. A decreased temperature, our P50 is less than 26.6. We have a decreased temperature. Well, that means that the oxygen is actually holding on. The hemoglobin molecule is actually holding on to the oxygen molecule even more. It has an increased affinity. So they all kind of tie together, okay? And it all goes to metabolism, cellular metabolism. We can talk about the oxyhemoglobin dissociation curve another time. But again, I really did want to just tell you about the importance of temperature and its inverse relationship relationship to the solubility of a gas. As temperature increases, the solubility of a gas decreases. As it decreases, the solubility of a gas increases. And that's your Henry's law. I hope that was helpful. The one part I didn't tell you about is why would temperature really be a big deal? Well, what does temperature really do? Well, temperature actually increases the kinetic activity of the molecules. As temperature goes up, kinetic activity of these molecules goes up, and that allows these oxygen molecules to escape, thereby decreasing the partial pressure of that gas in that given liquid. Okay, so you can see that? And so as temperature goes up, the kinetic energy goes up. There's a direct relationship. As this kinetic energy goes up, as temperature goes up, there's a decreased solubility, which allows this gas to escape, therefore decreasing the partial pressure of that gas in that given liquid, in which we were talking about blood or plasma. Well, I hope that helps you understand Henry's law and apply it to the other parts of the oxygenation analysis of a patient. And it's an important part, Henry's law. The volume of gas dissolved at a given temperature equals the solubility coefficient times the partial pressure of that gas above that liquid. And here we're looking at solubility coefficient, and then we could use it as O2, and the partial pressure of that gas above the liquid. The liquid could be plasma, and we're looking at the gas of O2, and we get that solubility coefficient of 0.0003. And if we know what the partial pressure is from a blood gas, we can make that formula from the PaO2. And now we have Henry's law coming back in reverse. Hopefully that helped, and I will be trying. Let me know how that was, if it was helpful, and I'll be looking to do some more videos in the future. Have a great night.